So our last section we're going to look at this week is radical functions. And what I did there is I created my own font. Like if I was going to create a font called the rad font, that's what it would kind of look like. That's pretty cool, huh? Yeah. All right. There's more. Don't worry. So radical functions. So this is a different kind of function than what we did yesterday. It's not rational. Rational is when you have a fraction and you've got a polynomial in the top and the bottom. Okay. These are radical functions. Radical functions have some kind of root in them. Okay. It doesn't have to just be a square root. It could also be a cube root, fourth root, any root. Okay. Radical functions have a root in them. So what I want to do is talk a little bit about all the parts of what I just circled. Okay, there's a radical expression, there's a radical symbol, there's a radicand, and there's an index. In the one I circled in green, it's not written, so we assume it to be something. In the one over here, the index is written because it's needed. So we'll talk about what all those pieces are called now. So anytime that you write an expression that looks something like that, the number that you put on the outside right there has to be a number bigger than 1, and it can't be a decimal or a fraction. It has to be an integer. Okay, so it can be a 1, 2, well, it can be a 2, 3, 4, 5, 6, and any number 2 or higher. No decimal. That number that you put right there is called the index. What the index tells you is what kind of root you're working with. So if you see a 3 in the spot for the index, that means it's a cube root. If you see a 5, it's a fifth root. If you don't see a number at all, I'm going to talk about that in a second, but that's a square root. So whenever we don't see an index, it's always assumed to be a 2. That entire thing that I have circled, circle in a different color in red, that's called a radical or a radical expression. It's not an equation because there's no equal sign. This is a radical equation because it has an equal sign. This is a radical expression. The radicand is the part of the radical that is underneath the root symbol. Okay. So there's different names for that. What's written in black there, you can call it the root symbol, the radical symbol, the radical sign. It's all just different names for the same thing. Okay, but this is called a radical sign or radical symbol. So if I write something like this, and I asked you what the radicand is, you would say 3x. The radicand is the part under the radical sign. And if I said, what's the index, you would say 4. Okay, so index, radicand, radical expression, the whole thing. Any questions on those terms? Now, a lot of times you just see a radical sign and you don't see an index, and that's because we always assume it to be a 2 if it's not written. So that means square root. Even though you don't see a 2 there, you could put a 2 there. We usually don't. But that means square root of 16, which is 4. Now, let's say that I wanted to say this, but I didn't want it to have a radical sign in it. There's a power you can raise 16 to. Bless you. And it's exactly the same as taking a square root. Does anybody know what number could go in that box? And it would give me the same answer as the square root of 16. Yep.
1/2.
1/2. Yep. So if you take that, take the square root of 16, you get 4. If you take 16 to the 1/2 power, you also get 4. Yep. It's the same thing. There's another example. If you wanted to write the square root of x minus 2, but for some reason you're not allowed to use that symbol, you can do it without the symbol and just say to the 1/2 power. Does anybody have a guess what power would be the same as a cube root? The 1/3. Yep. How about what power would be the same as a 5th root? 1/5. And this one kind of shows the reason why you might change something from having a radical sign to having a fractional exponent. Okay, look at this last one. X to the 4th, and you were taking the 5th root. Well, we changed this part, that's the 5th root, to be a 1/5 power. So we changed what's circled in red there to what's circled in red there. Now, when you have a power raised to another power, what do you do with your two powers? Yeah?
You combine them together.
How do you combine them?
Like the 4/5.
Right, you multiply them. When you have like 3 squared to the 4th, that really means 3 to the 8th. You take your two powers and you multiply them. So by changing this root into an exponent, it allows us to simplify to x to the 4/5. All right, so that's just a simpler way of writing what we started with. The top two, I wouldn't say either one is simpler or more complex. I would say square root of x minus 2 to the 1/2. Same thing. But I would definitely say this is simpler than what we started with. Okay. Any questions on that? All right, so we are going to have some questions that ask us to solve for what's called the principal root. Okay. So to understand what that means, we kind of have to understand just what happens when you take a square root. Let's use that as an example. When I type in the square root of 9, the calculator tells me 3. What the calculator did there was the principal root. There is another number times itself, which also gives me 9. What's that number? Yeah?
-3.
Right, -3 times -3 is also 9. The calculator didn't give me that one because that's not what the calculator is set up to do. Right? The calculator always gives you the principal root. When you take a root, there's always as many answers to the question as the index. So if you are doing a cube root problem, there are 3 answers. If you're doing a 5th root problem, there are 5. Not all of them are real. Some are imaginary. Okay, we're not focusing on imaginary in this section, so we're not going to worry about all the different answers. We're just going to worry about the principal root. So how do you do a principal root if, say, the exponent is, if the index or the exponent is an odd number? Okay, so let's say you had a problem like this. X cubed equals 64. And I asked you to solve that. We kind of had one, I think, similar to that in homework last night. And we actually went over it. We have a power of 3. What is the opposite of cubing something? Yeah?
Cube root.
Cube root. So where something like this would come up is in an equation like that. If you take the cube root of each side, cube root and cube cancel, And now you have x by itself, and you have cube root of 64. So now you have something just like I circled up here. That's when this would come up. When you're solving an equation that has a power, and you have to do a root to get rid of that power. Now, how do you write the answer to that? Okay. All we have to do is pretty much just type it in on the calculator. The only thing I don't want you to worry about is imaginary answers. Okay? Technically, when you do a cube root, there are two answers here that are imaginary. We're not dealing with those in this section. So I'm just pointing out, all I want you to do is find the real answer. So to type in a cube root, there's a couple ways you can do it. I'm going to show you a way that works for any root. First thing you do is you type in your index. So we're doing a cube root, so we're going to start with a 3. Then you're going to press math, and then you're going to go to option 5. Option 5 will take that 3 that you typed in and turn it into the index. And now you can put in 64, and you get an answer of 4. Again, not the only answer, but it is the real answer, and that's the answer I want. Okay. Any question on that one? Yeah.
What would the other answers be, like other than negative?
They would be imaginary. So I could show you what they are, but just since we're not going to get into it today, and you don't need to know that for the test, I just don't want to waste a few minutes doing something you don't need right now. We might talk about those more later on, maybe, I'm not sure, but it wouldn't be till a much later chapter. Yeah. But they would be imaginary. I'll tell you that much. Yeah.
Can you show us how to type it in?
Yeah. So to type in the cube root, you press the index, you press math, and then you go to option 5. So index, math, option 5. And it doesn't just have to be a cube root. The index could be any number. I don't know what happens if you try a decimal, because technically you're not supposed to do decimals. So the 2.6th root, let's see what happens. Okay, I'm not 100% sure what's going on. I'd have to figure it out. I don't know what that is. But our index is always it's always an integer. I just wanted to try that. What happens if you do an index of 1? I'm curious to see. Because really, when you do an index, it has to be a number higher than 2. So I wonder if that's actually going to square it and give me 256. Nope, it gave me back the same. Oh, it gave me back the same answer. Huh. Okay. All right, so that's for odd roots. Okay. For even roots, there's a condition on the radicand. I didn't show you, but with an odd root, I could have typed in a number like this. That wasn't our problem. But I can type it in and it works fine. So I can take an odd root of an even radicand, of a positive radicand or a negative radicand. You can do odd roots of any numbers you want. But with even roots, let's try to do a square root of -8. Well, if I try to do it and stick with the real number system, which is what we're doing, it tells me that you get a non-real answer. So when you are dealing with any kind of even root, square root, fourth root, sixth root, the number under the radical sign has to be greater than or equal to 0. That number right there.
Sorry, I was about to sneeze.
Okay, that's only if the index is even. What would happen if it wasn't greater than or equal to 0? You're going to get imaginary answers. And it's just not something we get into. All right. So when would this kind of thing come up with an even root? Well, let's say you have this. to get rid of that exponent of 2, you've got to do the opposite of squaring on each side. What's the opposite of raising to the second power?
Square root.
Square root. Square root. Square root. Those cancel out. And now you're left with x equals the square root of 36. You're left with something just like we circled up here. X equals square root 36. First, I'm going to check it. Is my radicand greater than or equal to 0?
Yeah.
Yes, then I can definitely solve this problem. If that was a negative number, I would be stopping here and saying that there is no real solution. Not that there isn't a solution, there is, but it's not real. And when you're dealing with a principal root, they want real answers, not imaginary. All right, so now we would solve that. And when we take the square root of 36, there are 2 answers that would give us 36. But I want the one that's not negative. So what number times itself gives you 36, and it's not negative? Yeah? Positive 6. If you were thinking negative 6, yes. Negative 6 times itself is also 36. But that's not the principal root. The principal one is not negative. Okay. Any questions on that? So a few more restrictions when you're dealing with even roots. And those restrictions help us to avoid imaginary numbers. Okay? The radicand has to be 0 or higher. With odd roots, that's not true. Radicand can be anything you want. All right, now let's look at this. So we're going to look at what happens when we take a square root. And I want to figure out, does taking a square root make the number smaller or larger? And again, if you look at what I did there, smaller is smaller, and larger is larger. Yeah. All right. So let's try this one. So if x is 4, what would be the square root? We'll just do the principal root. What's the square root of 4?
2.
2. So in that case, when we took the square root, did it get smaller or larger?
Small.
Got smaller. Okay. Let's try 18. Okay. That, not a nice answer, but we could just type it in. 4.24. So what does it look like happens when you take the square root? Okay, it looks like it gets smaller. Let's try this one. What's the square root of 1? 1. What happened there?
Stays the
Stay the same. All right, so maybe when you take a square root, it either gets smaller or it stays the same. Well, let's try this one. The square root of 0.5. 0.71. So what happened that time? Got bigger. So when you take a square root, does it get smaller or larger? Well, it depends. Both could happen. Depends on the number you're taking the square root of. Right. Does anybody think they know what number you can take the square root of and it will always get smaller?
Anything above 1.
Anything above 1, if you take the square root of it, it gets smaller. Anything, if it is 1, it stays the same. And then remember, you can't go negative because square roots of negative numbers don't work. Well, they're imaginary. Anything, if you take the square root of any decimal between 0 and 1, it will get bigger. Square root of 0.2 is 0.45. So between 0 and 1, it gets bigger. Exactly 1 stays the same. Bigger than 1, it gets smaller. Any question on that idea? Okay. So let's graph a couple even square roots just so you can see what they look like. I'm going to do a square root, a 4th root, and a 6th root, all on the same graph. So let's do square root of x. Let's do 4th root of x. And let's do 6th root of x. All even roots have kind of the same look to them. Now let's do zoom 6. That's your square root. That's your 4th root. And in black is your 6th root. In terms of the directions that all those roots go in, what direction do you notice they all go in?
Also.
They all go to the right. They all go to the right. So I'm going to eliminate looking at these quadrants so I can just zoom in a little bit more on quadrant 1. So it doesn't go negative. Doesn't go negative, and it didn't go up that high. Square roots are pretty flat. They're not flat. They do curve, but they look kind of flat. Okay, so there's your square root. Especially the further you go, the flatter it starts to look. And the higher the root, that's a 4th root, it starts to look flatter sooner. And there's your 6th root. So that one's going to start to look the most flat out of all 3 of them, the further to the right you go. But again, it is not flat. It does keep going up very slowly. All right, so let's look at that graph. And is there any coordinate that it looks like the even roots all go through? Anybody see a location on there that all 3 of those curves pass through? Yep. 1 comma 1. Yep, 1, 1. That is a point that is common to all even roots. 1, 1. And there's another point. It's kind of hard to see because the calculator doesn't do a great job with it. Does anybody think they see another point that they all pass through?
0, 0.
Yeah, they all pass through 0, 0. Okay. All right. Yeah, they all pass through 0, 0. So those 2 points are common to all even root graphs. 1 comma 1 and 0 comma 0. And when I say it's common, I mean if you don't shift it or do anything to it. Yes, if you took this and you shifted these graphs up or down, then these 2 points would shift up or down with them. But if you don't shift them, those points are common to all the graphs. Okay, the other thing I want to look at is the domain. These graphs only went to the right. So when you're dealing with a square root function, or a 4th root, or a 6th root, or an 8th root, any root that's even, what's the smallest number that I could plug in here for x? 0. You can take the square root of 0. A lot of people get that mixed up with dividing by 0. Can't divide by 0, but you can definitely take the square root of 0. Get 0. So 0 is the smallest number you can plug in. And what's the highest number?
Infinity.
Infinity. So that's your domain. 0 to infinity. Now, if you do something like this, let's say you had square root of x minus 2, that changes it a little bit. You can't plug in 0 now for x. Because if you plugged in a 0, what would you get under the radical?
-2.
Yeah, you can't do the square root of a negative. So in this one, you could plug in any number 2 or higher. In that one, it's 0 or higher. So when I say the domain is 0 to infinity, I'm talking about if you don't do a transformation like that. Okay? We will look at transformations, but not yet. Now, how about the range? Look at the blue, the red, and the black. How low do all of those graphs go?
0.
They go as low as 0. And how high will they go?
Infinity.
They will go to infinity. It doesn't look like, especially the black one, it doesn't look like it's going to keep going up forever, but it does. Right? It's just a very gradual going up. Alright, so that's just a couple facts about even roots. Any questions on that? So that's even. What's the other other kind of root you think we're going to look at? Odd. Okay, so let's type in a few odd roots. I'm just going to clear out that one, and I'm going to change my index to a 3, and I'm going to change my index to a 5. So I'm going to do a cube root and a fifth root. And I'm going to do zoom 6. Odd roots have they have a different look to them. Okay, so let's look at some odd roots. All right. Probably help if I zoom in a little bit. Let me set my y min and max to go like -4 to 4. I think that'll show it a little better. First of all, they are connected. It looks like they almost kind of skip a little in the middle. It's because it's getting steep, but they should be continuous. You don't lift your pencil the whole time you draw it. Okay. So what do you notice as a difference between the even root and now the odd root? What's something that's really very different between the two? Yeah?
The odd root has the negative quadrant.
Yeah, the odd root goes to the left and the right. Right? The odd roots go in both directions. Even roots only go in one direction. Yep. So that's a big difference. Let me zoom in a little bit more. Let's go -3 to 3. Because I want you to try to see the points that the odd roots have in common. I don't think you can see it real well from there. Okay, there are 3 points that odd roots all have in common. Let's put this here. Anyone think that they see the 3 points? I can make that a little bigger. Yeah?
-1, 0.
Yeah, -1, -1. It's a point right there. 0, 0, and I know it looks a little funny, but the black one should look more like that. It shouldn't be a gap in the middle. So -1, -1, 0, 0, and 1, 1. Those are 3 points that are common to all odd roots. Okay. So we got that. And what about the domain? How far left and right does it look like an odd root goes?
-infinity to infinity.
Yeah. So the domain is all real numbers, which means you can take the odd, you could do a cube root of any number, positive, negative, or 0, any number you want. So no restriction. So it goes left and right forever. How about up and down? How far up and down does it look like odd roots go? What is it?
Negative infinity to infinity as well.
Negative infinity to infinity. Yep, they're going to go left and right forever, and they go up and down forever. It doesn't look like, especially the black one here, that it's going up and down forever, but it is. It's just a very gradual up. But that's always the domain and range for any odd root that you draw. Doesn't matter if you shift it up, shift it down, shift it left, stretch it, compress it. It's always going to go left and right forever. It's always going to go up and down forever. You cannot change that with an odd root. So that's the general idea of what odd and even roots look like. Important thing is you understand an even root goes in one direction. We can flip it. Like you can do a reflection to make it go the other way. But the point is it only goes in one direction. Odd root goes in 2 directions. Okay, and the last thing I think we'll look at is a transformation problem. Okay, I'm just going to copy that over here so I've got some more space. So the transformations that we do are exactly the same as the transformations we've studied in every section we've done all year when we've talked about transformations. When I talk about being inside the function, I'm talking about this. What's that part called that I just put a box around? Remember the name of it? Begins with an R. Get my back. Yeah,
Radicand.
that's the radicand. So when I talk about being inside the root, I'm talking about the radicand. All right? So first, let's talk about what the A and the B do. So the A is inside the function, and it's either addition or subtraction. What type of transformation do you get when you do addition or subtraction? A and D are both this kind of transformation, but A is on the inside, so it'll go one way, and D is on the outside, so it'll go a different way. Which way does A move your graph? Yeah?
Left or right?
Left or right. So that is a horizontal shift. Which way does plus move the graph?
Left.
Yes, it's the opposite. Plus is going to move it to the left, and minus moves it to the right. Okay, so that's A. Now B is still inside the red box. It's still in the radicand, so it's going to have something in common with the other one that we just did. But now it's multiplication instead of addition or subtraction. So what do you think B is going to do?
Stretch.
And what kind of stretch? Because it's still on the inside.
Vertical.
No, it's going to be horizontal because it's still on the inside. Anything that's in the red box is horizontal. Adding or subtracting is a shift. Multiplying is a stretch, but it's backwards. So if you had something like the square root of 3x and you wanted to describe that, that's a horizontal stretch by 1/3. And you might be like, well, wait, you put in a bigger number, but it made it smaller? Yes. The bigger you make that number, the smaller the graph gets. If you had a small number, like square root of 1/2x, that's a horizontal stretch. But it's a small number, so it's actually going to make it bigger. How much bigger do you think 1/2 would make it?
2.
2. It actually doubles it. Horizontal stretch by 2. So the horizontal stuff is always backwards. Yeah. Let's put a box around that. There's your horizontal stretch. And there's your horizontal shift. Okay, now C. C is like B. It's multiplication in front, but it's now outside the box. So what kind of transformation do you think C is?
Vertical stretch.
That's vertical because it's on the outside, stretch because it's multiplication. Okay, there's not much to say about C because it's not backwards. If C is 5, you'd say vertical stretch by factor of 5. If it's 1/3, you say stretch by 1/3. Vertical stretch is not backwards. You do it just the way it's written. And how about D? It's like A, it's going to be addition or subtraction, but now it's outside the box.
Up or down?
That's your vertical shift. and it's not backwards. Positive is up, negative is down. Now, what would happen if B is a negative? Does anybody remember what a negative causes your graph to do? Flip. And since B has to do with horizontal stuff, that would be a horizontal flip, or horizontal reflection. So it's a horizontal reflection. Some people say it over the x-axis. I'm sorry, over the y-axis. So if you said flip over the y-axis, that's the same thing as horizontal. You're flipping left to right. Now, if C is negative, if C is negative, that's also going to be a what? What do you think?
Vertical reflection.
That's also going to be a reflection, but since C has to do with vertical, it's a vertical reflection. Yep. And vertical reflection, that would mean you flip up to down, which is over which axis?
The x-axis.
That's over the x-axis. Okay, so that chart pretty much describes, not that chart. There it is. A little smaller. So that chart right there, that describes everything that can happen in a transformations of a radical. All right. So let's keep that chart up and try this one. So it says explain how to sketch the square root of x minus 2, and the graph you would be starting with is the square root of x. So the first thing to understand is you'd never be comparing like a square root to a cube root. You always have to compare the same index to each other. How many transformations are in this one? Just one. What is that? What is that minus 2 going to do? Horizontal shift right 2. Yep. That's it. How about that one? Square root of x plus 3. Left 3. Yep. So shift left 3. And the last one, I'll give you a hint. You always want to think of it in standard form. Standard form means the x comes before the number. So I rewrote it so that x is before the number. How many transformations are there?
2.
2. What's the plus 3 going to do?
Shift left 3.
Yep, that's a shift left 3, actually the same as the one above it. Bless you.
Thank you.
And what's the negative in front of the x going to do?
Horizontal reflection.
Yep, that's a negative for the b, that's a horizontal reflection. Or you could say reflect over y-axis. And we can practice a few more transformations tomorrow too. Just make sure you have that table. Okay, so that's a good point to start. Okay, so let me adjust that a little bit. So 255. We're just going to go up to, up to 14. So 5, 6, 12, 14, and also do number 9. Okay, so 5, 6, 9, 12, and 14. Okay, and then tomorrow we'll finish that up.